All right, let's talk about the magic happening inside your computer. Ever stop to think about the secret sauce that actually makes it work? Today, we're going to pull back the curtain on the single most important piece of software running on your machine, something you use every single second, but probably never think about: the operating system. And it all starts with one simple click.
Seriously, think about it. You double-click an icon to launch a program, open a file, whatever. It just happens, right? It feels instantaneous, almost like magic. But behind that one simple action, there's this incredibly complex dance happening between your hardware and software. So what's really going on in that split second? Well, there's a hidden conductor making it all happen.
And that conductor, the hero of our story, is the operating system, or OS. The best way to think about it is as the master translator and manager that sits right between you and the raw, complicated hardware of your machine. It takes your clicks, your keyboard taps, all your commands, and turns them into a language the hardware can actually understand. It's basically conducting the entire digital orchestra.
Now, to really appreciate the slick OS you have on your laptop or phone today, we need to jump in a time machine. Back in the day, the first computers were gigantic, ridiculously expensive, and pretty slow. Wasting even a single second of their processing time was a huge deal. So the first big problem they had to solve was, how do we keep this insanely expensive machine busy 100% of the time?
The answer they came up with was something called batch processing. And honestly, it's a lot like doing laundry. An operator would literally take a whole bunch of jobs, group them together based on what they needed, all the whites in one pile, all the colors in another, and then feed them to the computer one batch at a time, usually with punch cards. There was absolutely zero user interaction. You drop off your job and maybe come back hours or even days later to get your results. It was all about squeezing every last drop of performance out of that CPU, not about making it easy for you.
So batch systems were efficient for the machine, sure, but for people, yeah, not so much. You couldn't just sit down, type a command, and get an answer right away. Fixing that problem led to a totally revolutionary idea called time sharing, and it completely changed the way we interact with computers forever.
I mean, the difference was like night and day. With batch systems, it was strictly one job at a time, from start to finish, with zero input from the user. Time sharing flipped that whole idea on its head. It was built from the ground up to be interactive, letting lots of people connect to the same powerful computer all at once. And it did this by cleverly slicing up the CPU's attention.
So how in the world did it create this illusion that it was doing a million things at once? The magic here is a concept called the time quantum, or a time slice. Basically, the CPU gives a tiny fraction of a second. We're talking like 5 nanoseconds to your text editor. Then, boom, it switches and gives 5 nanoseconds to your web browser. Then, boom, 5 nanoseconds to your music player. It cycles through all these programs so incredibly fast that from your perspective, it feels like everything is running at the exact same time. It's an illusion, but it's a brilliant one.
And that fundamental idea, an OS managing and sharing resources, is the direct ancestor of the unbelievably powerful systems we all use today. From the phone in your pocket to the massive data centers that power the internet, the core principles are exactly the same. They've just been scaled up to a degree that is absolutely mind-boggling. So today's systems come in a few main flavors, and each one is built for a specific kind of job. You've got your personal computer systems, think Windows, macOS, all designed for user convenience. Then for serious number crunching, you have parallel systems, which pack multiple processors into a single box. Distributed systems take that a step further, linking a bunch of separate computers over a network so they act as one giant system. And finally, for jobs where timing is absolutely critical, you've got real-time systems. Now, people get parallel and distributed systems mixed up all the time, but the difference is actually pretty simple. A parallel system is like having one grain with multiple cores. Everything is super tightly connected, sharing the same memory, the same master clock. It's incredibly fast because all the communication happens internally. A distributed system, on the other hand, is more like a team of individual computers working together. Each one has its own private memory and its own clock, and they talk over a network. It's a bit slower to communicate, but the advantage is you can scale it up to a massive size. And when we're talking about those real-time systems, there's a crucial difference you need to know. In a hard real-time system, think about the flight control system on an airplane, Missing a deadline is not an option. It's a catastrophic failure. The task has to finish on time, every time. But in a soft real-time system, like when you're streaming a video, missing a deadline isn't great. You might get a little buffering, but the whole system doesn't come crashing down. The quality might dip for a second, but it keeps on going. Okay, so we've covered the history, and we've covered the high-level types. Now it's time to pop the hood and take a look at the core components that make up the engine room of pretty much any operating system out there.
At its heart, every single OS is a master manager. It has to juggle all the programs that are running. That's called process management. It's the bouncer that decides who gets to use the computer's precious short-term memory, or RAM. It keeps track of all your files and folders through its file system. It handles every single time you press a key or move your mouse with I/O management. And then, wrapped around all of that, is security, which is there to protect the whole system from going haywire.
Let's just zoom in on process management for a second. Imagine you have two programs trying to access the same piece of data at the exact same time. That's a recipe for digital chaos, right? This is known as the critical section problem. And the solution requires three key things. First, mutual exclusion, which just means only one process gets access at a time. Second, progress, to make sure no process gets stuck waiting forever. And third, bounded wait, which guarantees a process won't have to wait an infinite amount of time. This logic is what keeps all your data from getting corrupted.
So, on top of just managing things, the OS also provides this amazing toolkit of ready-made services. It handles all the complex stuff like executing programs, talking to your printer, detecting errors, you name it. The real benefit here is that it lets software developers focus on building cool apps instead of having to reinvent the wheel and write code for these basic functions every single time.
Okay, so we've got our applications on one side, and we've got the super powerful OS kernel on the other. But how do they actually talk to each other? There has to be a formal, secure way for a simple program to ask the all-powerful OS for a favor. And that brings us to the last and maybe most important piece of the puzzle.
That formal, secure gateway is through what we call system calls. And this quote from the source material nails it perfectly. System calls are the only entry points into the kernel's system. Let that sink in. It means if a program wants to read a file or send data over the network or do anything important, it can't just do it directly. It must make a formal request through this single, heavily guarded gate. This is absolutely fundamental for keeping a system stable and secure.
And hey, this isn't some abstract theory. These are the actual commands that developers use every single day. You can even see how different operating systems handle the same job. On Windows, if you want to create a new process, you use create process. But in the Unix world, which includes Linux and Mac OS, the command is fork. The names are different, but the core idea is exactly the same. It's a regular program respectfully asking the OS kernel for permission to do something.
So there you have it. When you really step back and look at it, the story of the operating system is a story of constant evolution. It started with batch systems that were just chasing raw machine efficiency. Then it evolved with time sharing to bring people into the loop. And today, it manages everything from our phones to the global cloud. And that leaves us with one final big question. In a world that's heading towards AI, quantum computing, and the Internet of Things, what's the next great problem that our operating systems are going to have to solve?